In mathematics, church encoding is a means of representing data and operators in the lambda calculus. The data and operators form a mathematical structure which is embedded in the lambda calculus. The church numerals are a representation of the natural numbers using lambda notation. The method is named for Alonzo Church, who first encoded data in the lambda calculus this way. Terms that are usually considered primitive in other notations are mapped to higher-order functions under church encoding. The Church-Turing thesis asserts that any computable operator can be represented under church encoding. In the untyped lambda calculus, the only primitive data type is the function. The church encoding is not intended as a practical implementation of primitive data types. Its use is to show that other primitives data types are not required to represent any calculation. The completeness is representational. Additional functions are needed to translate the representation into common data types for display to people. It is not possible in general to decide if two functions are extensionally equal due to the undecidability of equivalence from Church's theorem. The translation may apply the function in some way to retrieve the value it represents, or look up its value as a literal lambda term. Lambda calculus is usually interpreted as using intentional equality. There are potential problems with the interpretation of results because of the difference between the intentional and extensional definition of equality. Church numerals. Church numerals are the representations of natural numbers under church encoding. The higher-order function that represents natural number n is a function that maps any function to its n-fold composition. In simpler terms, the value of the numeral is equivalent to the number of times the function encapsulates its argument. All church numerals are functions that take two parameters. Church numerals 0, 1, 2 are defined as follows in the lambda calculus. Starting with 0 not applying the function at all, proceed with 1 applying the function once. The church numeral 3 represents the action of applying any given function 3 times to a value. The supplied function is first applied to a supplied parameter and then successively to its own result. The end result is not the numeral 3. The function itself, and not its end result, is the church numeral 3. The church numeral 3 means simply to do anything 3 times. It is an ostensive demonstration of what is meant by 3 times. Calculation with church numerals. Arithmetic operations on numbers may be represented by functions on church numerals. These functions may be defined in lambda calculus, or implemented in most functional programming languages. The addition function uses the identity. The successor function is beta equivalent to. The multiplication function uses the identity. The exponentiation function is given by the definition of church numerals. In the definition substitute to get and, which gives the lambda expression. The function is more difficult to understand. A church numeral applies a function n times. The predecessor function must return a function that applies its parameter n1 times. This is achieved by building a container around f and x, which is initialized in a way that omits the application of the function the first time. See predecessor for a more detailed explanation. The subtraction function can be written based on the predecessor function. Table of functions on church numerals. Note that in the church encoding, translation with other representations, most real-world languages have support for machine-native integers. The church and unchurch functions convert between non-negative integers and their corresponding church numerals. The functions are given here in Haskell, where the corresponds to the lambda of lambda calculus. Implementations in other languages are similar. Type church are equals to a church. Integer to church 0 equals f2 x to x. Church n equals f2 x to ffx. Unchurch church integer to integer. Unchurch cn equals cn0. Church booleans. Church booleans are the church encoding of the Boolean values true and false. Some programming languages use these as an implementation model for Boolean arithmetic. Examples are Smalltalk and Pico. Boolean logic may be considered as a choice. The Church encoding of true and false are functions of two parameters. True chooses the first parameter. False chooses the second parameter. The two definitions are known as Church booleans. This definition allows predicates to directly act as if clauses. A function returning a boolean, which is then applied to two parameters, returns either the first or the second parameter, evaluates to then clause if predicate x evaluates to true, and to else clause if predicate x evaluates to false. Because true and false choose the first or second parameter, they may be combined to provide logic operators. This is only a correct implementation if the evaluation strategy is applicative order. This is only a correct implementation if the evaluation strategy is normal order. Some examples. Predicates. A predicate is a function that returns a Boolean value. The most fundamental predicate is, which returns if its argument is the Church numeral, and if its argument is any other Church numeral. The following predicate tests whether the first argument is less than or equal to the second. Because of the identity, the tests for equality may be implemented as Church pairs. Church pairs are the Church encoding of the pair type. The pair is represented as a function that takes a function argument. When given its argument, it will apply the argument to the two components of the pair. The definition in lambda calculus is, for example, list encodings. An list is constructed from list nodes. The basic operations on the list are, three different representations of lists are given. Build each list node from two pairs. Build each list node from one pair. Represent the list using the right fold function. Two pairs as a list node. A non-empty list can implemented by a Church pair. First contains the head, second contains the tail. However, this does not give a representation of the empty list, because there is no null pointer. To represent null, the pair may be wrapped in another pair, giving three values. First is the null pointer. Second, first contains the head. Second contains the tail. Using this idea, the basic list operations can be defined like this. In a nil node, second is never accessed, provided that head and tail are only applied to non-empty lists. One pair as a list node. Alternatively, define where the last definition is a special case of the general. Represent the list using right fold as an alternative to the encoding using Church pairs. A list can be encoded by identifying it with its right fold function. For example, a list of three elements x, y and z can be encoded by a higher order function that, when applied to a combinator C and a value n, returns cx. Derivation of predecessor function. The predecessor function used in the Church encoding is, to build the predecessor we need a way of applying the function one fewer time. A numeral n applies the function fn times to x. The predecessor function must use the numeral n to apply the function n one times. Before implementing the predecessor function, here is a scheme that wraps the value in a container function. We will define new functions to use in place of f and x, called encodings. The container function is called value. The left-hand side of the table shows a numeral n applied to encodings. The general recurrence rule is, if there is also a function to retrieve the value from the container, then extract may be used to define the same num function as. The same num function is not intrinsically useful, however, as inc delegates calling of f to its container argument. We can arrange that on the first application inc receives a special container that ignores its argument, allowing to skip the first application of f. Call this new initial container const. The right-hand side of the above table shows the expansions of n inc const. Then by replacing init with const in the expression for the same function, we get the predecessor function, as explained below. The functions inc, init, const, value and extract may be defined as, which gives the lambda expression for division. Division of natural numbers may be implemented by calculating takes many beta reductions. Unless doing the reduction by hand, this doesn't matter that much, but it is preferable to not have to do this calculation twice. The simplest predicate for testing numbers is 0, so consider the condition. But this condition is equivalent to not. If this expression is used, then the mathematical definition of division given above is translated into function on church numerals as desired. This definition has a single call to. However, the result is that this formula gives the value of. This problem may be corrected by adding 1 to n before calling divide. The definition of divide is then. Divide 1 is a recursive definition. The Y combinator may be used to implement the recursion. Create a new function called div by in the left-hand side. In the right-hand side, to get then, where, gives, or as text using, for, divide equals dfx, n. For example, 9/3 is represented by divide using a lambda calculus calculator. The above expression reduces to 3, using normal order, f, x, f, signed numbers. One simple approach for extending church numerals to signed numbers is to use a church pair, containing church numerals representing a positive and a negative value. The integer value is the difference between the two church numerals. A natural number is converted to a signed number by negation is performed by swapping the values. The integer value is more naturally represented if one of the pair is 0. The only 0 function achieves this condition. The recursion may be implemented using the Y combinator. Plus and minus addition is defined mathematically on the pair by. The last expression is translated into lambda calculuses. Similarly, subtraction is defined, giving, multiply and divide. Multiplication may be defined by. The last expression is translated into lambda calculuses. A similar definition is given here for division, except in this definition, one value in each pair must be 0. The divs function allows us to ignore the value that has a 0 component. Divs is then used in the following formula, which is the same as for multiplication, but with mult replaced by divs. Rational and real numbers. Rational and real numbers may also be encoded in lambda calculus. Rational numbers may be encoded as a pair of signed numbers. Real numbers may be encoded by a limiting process that guarantees that the difference from the real value differs by a number which may be made as small as we need. The references given describe software that could, in theory, be translated into lambda calculus. Once real numbers are defined, complex numbers are naturally encoded as a pair of real numbers. The data types and functions described above demonstrate that any data type or calculation may be encoded in lambda calculus. This is the Church-Turing thesis.